Hello honors physics students. Okay, let's get started today with a problem in our problem set, the practice problems number 33. So go ahead and read it, try it completely on your own. You have all the numerical answers there, so you should be able to solve it no problem. And then come back to see just a couple pointers I'm going to give you, and then also about drawing the voltmeter. Okay, so first, of course, you want to identify what sort of arrangement this is, and ideally you see that they're in series. There's only one path. If you follow an individual proton coming out of the battery, it goes to the 15 ohm, then it must go through the 10, then it must go through the 6 before coming back to the negative terminal. That's a great indication, they're in a series connection. So here's a lot of the values, right? So we have a total of 15, 25, 31 ohms of resistance there. So 10 volts for 31 ohms gets a total current of 0.323 amps. And then hopefully you're doing what I was showing you previous day's videos that you just draw the current on there. We always like to draw to I total as coming out of the battery. You can draw it here going into the battery as well. And this is only one path, all 0.323 amps is going to pass through here, pass through here, pass through here, and then just a matter of just using Ohm's law. Delta V equals IR. This current times this resistance, this current times this resistance, this current times this resistance gets these individual voltage drops. Remember, those are the words we use: the voltage gain through the battery, voltage drop, voltage drop, voltage drop. How do we know things are working? Well, we know whatever it gains through the battery, it has to drop through the resistors. So if it gains 10 volts, it better lose a total of 10 volts by going through these three resistors. So if you add up these individual voltage drops, so they add up to about 10 volts. Yeah, it's off by a little bit, but that's because of some rounding issues. But try it on your own, just to make sure. You should see it's really, really close, and that's a really good indication things are working. Okay, so the other calculations, there's nothing really complicated there. Just pick the right equation. What about drawing the voltmeter? Well, it says to draw the voltmeter across the battery. Right? So we have to remind ourselves how our voltmeters connected. If you weren't sure, hopefully you look back at your notes. And we know voltmeters are connected in parallel, which means they're not part of the circuit. They have to be in parallel, in this case, across the battery. So I'm going to draw my voltmeter here. A voltmeter is the circle with a V. One wire is at one side of the battery, the other wire is on the other side of the battery, because remember, here's the positive terminal, here's the negative terminal. As long as it's this sort of arrangement where you have a junction here, a junction there, you have the voltmeter connected correctly. Can it be over here? Of course it can. Put the voltmeter over here and a wire here and a wire there. It's fine. I just put mine on the inside of the circuit, but on the outside of the circuit, space confined by the circuit. It doesn't really matter as long as it's one lead, one wire before the battery, one wire after the battery, one way or the other. It works. Okay, let's go over some homework. I'm going to shift over to the conceptual questions in the textbook, starting with number 2. All right, number 2 asks about given 3 light bulbs in a battery, sketch as many different circuits as you can. And just so you know, the correct number of circuits is going to be 7. There's actually 7 different unique arrangements, assuming identical light bulbs. Now, it doesn't actually say that. It actually gets a lot more complicated if they're not identical light bulbs, but it doesn't really say much about them. So we're just going to assume that all light bulbs are identical. There are actually 7 different arrangements. So if you didn't get 7, why don't you pause the video here and see if you can stretch your imagination and see if you can get all 7. Okay, so first I'm going to go through the standard ones. So I'm sure everyone got 3 resistors in series, right? One path here, 1, 2, 3 resistors, and 3 resistors in parallel, 1, 2, 3. Now, if your series and parallel circuits don't look exactly like mine, that's fine. As long as you have one of your circuit diagrams that has just one single path with all 3 resistors on it, and one circuit diagram with 1, 2, 3 separate paths with 1 resistor on each path, you're fine. Now, what you absolutely don't want is a short circuit. If you drew 1, 2, 3 paths, then you also have a wire extending over here. You've actually just short-circuited the entire circuit. So that's wrong. Get rid of that extra wire if you have that. Guys, some students just keep drawing paths and they forget about, oh, wait a second, I drew an extra path with no resistor on it. That's bad. That would not work at all. So make sure you get rid of that. Okay, so what are some other arrangements using all 3 resistors? Well, hopefully, if you used your imagination, you got something like this. Here we have 2 resistors with a junction there, which means they're in parallel, and then a single resistor that's in what sort of connection? Hopefully you see it's in series, right? If you watch an individual charge, comes out of the positive terminal of the battery, goes through maybe this resistor here, and then it must go through this resistor before coming back to the battery. That must be a series connection, or a charge that goes through this resistor, then also again has to pass through this resistor before going back to the battery. So here we have a compound connection. These two are in parallel with each other, and the combination is in series with this resistor. Now, what if you put this resistor over here? Does that change it? Is that a unique connection? No. Remember, you've done this before, specifically with the lab. When you swapped the positions of resistors in series, you noticed nothing different, nothing what's different about them, right? So if you have this resistor that's in series right after the battery or right before the battery, it doesn't matter. Either here or there, that means the exact same thing. Those are not two unique circuits, and you don't have to change it. If you did draw the resistor here as opposed to here, that's fine. What about this connection? Well, we've got a junction here, so we know it's parallel, but on one branch there are two resistors in what sort of connection? Right, series. And then on the other branch there's just a single resistor, right? So a charge comes out of the battery, gets to the junction, either takes this path and goes through a single resistor, or takes this path, goes through one, and then must go through the next resistor. That means these two are in series. This is another unique combination. Now, would it matter if we have two resistors on this path and one on this path? Would that be any different? No, it wouldn't. Remember, that's not any different at all. And again, you test this out in the lab by swapping the positions of the resistors in parallel. You know, really nothing was different about them. Okay, so we'll be looking at our four combinations here. One that is all three in series, one that is all three in parallel, a circuit that has two in parallel and one in series, or a circuit that has two in series here on one branch and one resistor on a branch all by itself. These are four unique combinations, and just sort of check them off your list and see if you got all four of those. But I did say there are 7. Alright, so it's a little bit of a tricky question, because it does say given 3 light bulbs in a battery, sketch as many different circuits as you can. It never said you had to use all the resistors, did it? Right? So that means that these 3 are also possibilities. Just one resistor, 2 resistors in series, and 2 resistors in parallel. So 1, 2, 3, 4, 5, 6, 7. Here are our 7 unique combinations, and again, this is assuming that all the light bulbs are of an equal resistance. Alright, let's move on to conceptual question number 4. Here we're looking for something that's going to be the same when resistors are connected in parallel, and I mean, it's really just a matter of looking it up in your notes, or this handy-dandy notes chart which I gave you, right? In parallel, what's the same? Oh, voltages are the same. So that's just choice 2, because our potential difference is just another name for voltage. Letter B asks about series. Okay, what's the same? Oh, it's going to be the currents are the same, right? Okay, so let's say currents, that's going to be choice 1 there. Alright, but then it said to consider a circuit justifying it with 3 and 5 ohm resistors, so let's draw that. Here's the 2 of them in parallel, that's letter A. And if we watch an individual charge that goes through the battery here, that's like our skier going up the ski lift, going up 12 volts, and then if it goes through this path and it comes back to the battery, well, if it gained 12, it must have lost 12. However, if instead it goes up the ski lift gaining 12 and takes this path, and then ends up back at the battery, it has to have lost all 12, and so we know that these 2 must have the same voltage drop with the same potential difference across them. Just go back to our ski resort analogy, it leads you through to the correct solution. About when they're in series, well, if they're in series, there's only one path there, and if you were to figure out the currents there for 12 volts for a total of 8 ohms means 1.5 amps, and since there's only one path, any charge that goes to the battery comes out here, and then goes to this resistor, and then must go to this resistor. There's nowhere else for them to go. The currents only change when there is a junction. If there's no junction, there's only one path, the currents must all be the same. That's why this is the correct answer here. This is why this is the correct answer here. It's not just a matter of memorizing, it's understanding why it happens, being able to explain it. Let's look at conceptual question number 6. Now we're looking at equivalent resistance. Alright, so we know if they're in parallel, what happens? Well, we know put more resistors in parallel, we get a smaller and smaller REQ. What's the correct choice? It's actually choice 2. REQ is actually less than any of the resistors. This doesn't tell you that, but we're going to come back to that. How about for letter B? If they're in series, well, putting more resistors is going to get larger and larger, which means it's going to be choice 1. REQ is greater than any of the resistors in the group. That's a little bit easier to see. So let's look at our circuits. And here's REQ for each of them. The series one is real simple, right? Just literally add them together. If you keep adding them together, there's no way REQ is ever going to be smaller. So of course, REQ is always going to be larger than any of the resistors in the group because you have to add them together. What happens here in parallel when you do a 3 and a 5 in parallel, either by doing the 1 over R1 plus 1 over R2 equals 1 over REQ, or, well, since there are just 2 of them, you can do your shortcut. You might want to practice doing that, right? The product over the sum, 5 times 3, 15, divided by the sum, 8, and I can't do that one in my head, but when you do it, you get REQ is 1.9. Here I'm using 2 sig figs. You look at the numbers in the problem, everything there is 2 sig figs, right? So I'm using 1.9. I'm sure you did also, right? Don't give me more than 2 sig figs. But the point here is you notice that 1.9 ohms is smaller than any of the original individual resistors, and that's always going to happen. That's just how the equation works when you do the 1 over R1 plus 1 over R2 and so on and so forth. No matter how many resistors there are in parallel, REQ will always be smaller than any of the individual resistors. Okay, let's go back into our problem set and we'll look at problem number 35. So, as usual, read the whole problem, try it completely on your own, and then come back to so I can give you some pointers in case you get stuck. The first thing you want to look at is what sort of connection we have. Is it series, is it parallel, is it compound? So ideally, first you see there's a junction here and a junction there, which leads you to believe maybe it's parallel, but then you say, wait a second, what about this 6 ohm resistor? And an individual charge that goes to the battery gaining 10 volts has to go through the 6 ohm resistor, and then before going back to the battery, it has to pass through something else, and so that means the 6 ohm must be in series with something. So this must be a compound connection. What's the 6 ohm resistor in series with, though? Is it in series with the 15? Is it in series with the 10? Is it not in series with either one? The 6 ohm is in series with the combination of these two. That's the only proper way to say it because of the junction here, right? Once a charge goes through the 6 ohm resistor, it doesn't have to go through the 15, it doesn't have to go through the 10. It has to go through one of them, but it doesn't have to go through one of the individuals, right? And so we can't say 6 is in series with either one, 6 is in series with a combination. So what do we do? Well, there's all sorts of ways to do it, but I think one of the easiest ways to do it is to take these two resistors out, the 15 and the 10 out. Imagine just finding REQ for those. They're in parallel, so you can do our shortcut, 15 times 10 divided by 15 plus 10, or do the 1 over business. And then what you want to do is you want to think about replacing these two with one single equivalent resistance. Remember, that's what REQ really stands for. Equivalent resistance. That you can put one resistor there and it'll do the same job as these two originals. You should be getting 6 ohms of equivalent resistance. So you can either just sort of imagine 6 ohms here or draw a 6 ohm resistor in there, or just redraw the circuit. I think these are a really good idea, especially as the circuits get more and more complicated, to actually redraw it, simplifying the circuit, taking the 15 and 10 out, replacing it with REQ of 6 ohms, and now you see it's very simple. 6 in series with 6, there's a total of 12 ohms of resistance in the circuit. REQ is 12 ohms. Great. That's usually a good first step. There are other things you might want to do, but finding REQ is usually a good first step, breaking it down, simplifying and simplifying and simplifying. Alright, so now we have 10 volts for 12 ohms. Real simple to find I total. It's going to be 0.833 amps, and then draw it on the circuit. Draw it on the original circuit, draw it on the simplified circuit, draw it on the circuit coming out of the battery. What should you do next? Well, if you follow these 0.833 amps, well, all those charges have to go through the 6 ohms. Here it's really easy to see. All 0.833 amps has to go through 6 ohms. And so if 0.833 amps goes through 6 ohms, what can you find? Well, you've got the current and the resistance. You can find delta V. You can find the voltage drop, right? It's got to be 5 volts. So what do you do next? Well, here it's pretty easy to see, right? Any charge that gains 10 volts has to lose a total of 10 volts. It just lost 5 through here. That means there must be 5 left for the 6 ohms. Gain 10, lose a total of 10. But that's not the real circuit. The real circuit's over here, right? Any charge that gains 10 has to lose all 10. So it gains 5 here, and then it either loses 5 through this resistor or 5 through here. Either one of them drops 5 volts. You say, well, how could that be? Remember, they're in parallel. An individual charge is either going to go through the 15 or the 10. So if you trace any path, gain 10, lose 5, it lost 10. Gain 10, lose 5, it lost 10. Because remember, this 6 ohms is representing this combination. Whatever this 6 ohms did, either one of these will have to do the same thing. Alright, so then what do you do? Well, look what we have. We have 5 volts for 15, 5 volts for 10 ohms. We can find the individual currents. I even wrote it, voltage over resistance, just like I told you to do. And so we can find the individual currents. So 0.833 amps is going to split up. 0.333 goes here. 0.5 goes there. What's our check? Well, look at this. 0.8333 and 0.5 adds back up to the 0.833. So 0.833, all of it goes here. It splits up through these two different paths. They come back together here, and all 0.833 amps come back through the battery. Alright, so what about drawing the ammeter? Well, it says the ammeter has to read the current specifically through the 6 ohm resistor. So where would you put it? Well, maybe you want to put it here, right? 0.833 amps just went through the resistor, and here it is in series, because we know ammeters are in series. But would it be any different if I put it there or there? No, right? That's still going to read the current through the 6 ohms because 0.833 amps goes here, goes to the 6 ohm resistor, and then splits and comes back together. So putting it here works as well. Putting it there works. So really anywhere, here or here or here or here, really anywhere that's just not on one of these branches, that's going to read the current through the 6 ohm resistor. Anything will work. I know it's a little bit tough to draw, to obscure the wire, because I want to make sure the wire doesn't actually go through the ammeter. I have the luxury of doing that on my picture here, but that's the idea. It could be here, or here, or here, or here, or here, or here, or here. Anywhere along there should be fine.